Okay. Today we have a very important lecture. Today we will be building on top of all of the concepts we've done so far and introducing we're really getting into how to use Python for data analysis and data cleaning. Last lecture we talked about various sources of data and the process of mining data. One thing that a lot of questions people had is understanding, we went through regular expressions very quickly. And some of you had some questions on when we would use regular expressions versus not use regular expressions. Can someone tell me why we use regular expressions? What's the purpose of regular expressions?
Data.
It's what?
Structure unstructured data, or parse data.
Yeah, it's more on parsing. So we can extract regular expressions in a nutshell allow us to recognize patterns in text. So if I'm looking at a large body of text, such as something on this page would be an example of unstructured data. Most of the data, at least as a process, we need to get the data from some sort of unorganized, some sort of raw format, unstructured format into a structured format, be it a tabular format, some sort of data structure that we can mine, process, parse, that we can work with in code. Computers, algorithms are very structured in the way that they deal with information. Humans, on the other hand, are completely unstructured in the way that they deal with information. And the irony is that information that's very easy for people to see, for people to read, to people to understand, is very difficult for computers to analyze and understand. And there's an irony that the human mind is very good at finding patterns that computers have a very difficult time, repeating. An example is facial recognition is a pretty difficult problem to solve, yet this is something that we do automatically without even thinking about it. Our brains are very, very, well wired to find specific patterns like facial recognition and recognizing a certain person, even in a very blurry photograph, or recognizing a person's voice. It's very difficult for computers to do the same thing. So in order to get computers to really effectively interpret information, we need to get that data into some sort of format that computers can understand. And this is what we call, this is a form of data mining in which we take unstructured information and we structure it into tabular formats into what we call data structures, dictionaries, and lists, so that we can better process, interpret, and perform calculations on that data. So last class we talked about really how that process works, converting unstructured data to structured data. This class will be talking about, once we have structured data, what do we do with it? What are the tools we use? What are the processes for really cleaning up a data set, analyzing a data set that's in what we'll call a tabular format? So before we do that, one of the key tools that we'll be using throughout this class is IPython. I sent a note today on Slack, but I want to at least sort of telegraph this so that this is clear, because we'll be using IPython a lot through this class. If you can, in your terminal, navigate to your DAT20 NYC folder and run the following command, IPython notebook. And I think I'm already running one. So when you run IPython notebook, you'll see Python, it may automatically load this directory. Some of you are using Anaconda. You can also get here through the Anaconda launcher. Anaconda comes with basically a graphical user interface that allows you that provides an interface for these commonly used commands, commonly used tools, particularly IPython and a variety of other tools. Regardless, you should be able to get to this page. If you go within lectures, lecture 4, you'll see there's this file with sort of a funky file extension, IPyNB. That stands for IPython notebook. And you'll see one called pandas.ipynb. if you click on it, you get something that looks kind of like this. This is what we call the environment of the IPython notebook. We've spent the last couple of lectures working with the Python console. The Python console works well for interacting with simple commands, simple operations. It's very useful for learning and exploring certain algorithms in Python. IPython takes that concept to the next level. IPython is really designed as a tool for communicating concepts in code. It's a means that I can actually run code in a notebook-like environment, almost like a web page, and I can document what I'm doing. I can visualize what I'm doing, and I have really it's an extension of it's an augmentation, an extension of the Python console. We also call the Python REPL. I can also, I'll open a new tab. I can also type IPython to get to the IPython console within my terminal. This has the same, I can't do the same visualizations as I can within the browser, but I can do, all the commands I have in Python I have, and I'll turn off the light so you guys can see it a little bit better. But all of the operations, all of the capability I have within the Python console, I also have within the IPython. All of the capability I have within the Python console, I also have within the IPython console. It's in fact a little bit nicer. It's colorized. I can get help. There's more documentation, and so there's a bunch of tools at my disposal that I have in IPython that I do not have in Python. We call this sort of an extension or a wrapper of the Python interface. It has all of the capabilities that the Python terminal has, plus some. So I want to give you guys a quick 5 minutes to at least get to this point. Make sure we're all on the same page. When you're on this page, we'll go through a quick tutorial. And you should be able to run all. In other words, you can run, you see all these code snippets, it'll run them, as if they're actual code. So it actually does, it does actually interact with the Python runtime and run the code that's embedded in this IPython notebook. So is there anyone who can't run this? Is there anyone who's unclear on any of this? Okay.
I'm not sure how you got there from the .20
So I navigated to the DAT20 directory in my terminal. Right? So you have, you should be able to navigate to this directory. And when you type IPython notebook, what do you get?
Well, I got it's launched.
Okay, great. So now you can navigate. Yeah. So now you can navigate within that. You can navigate to lectures, lecture 4, and you'll see a file with an IPyNB extension. It'll be called pandas.ipynb. Okay. Is anyone else having any issues with Python? It's okay if you don't. You're not up to date with the So navigate with the bar. So there's that bar for you. You're going to run across right now. So you can actually just do CD and then copy these. try to watch what happens when you press tab right now. Press tab. So you need to select from tab quickly. Press tab. It will actually automatically complete. Find it in the local repository. So if I type in DAT, right? See how I was finds it. So right now, change now this is also going to be tracked. So now it's going to be once that's
Keys are also. They started doing
Fair enough, yeah. Yes, he was. One of the songs. So I do think some good use of probabilities, and I think like long-term percentages are a better predictor of future performance. So this sample size, in the grand scheme of things, like the general. It's hard to say it shouldn't be too much. Like, you know, this guy's up for it. He's going to point to his stats and get literally 15 ball position. So
now I go here.
I'm his agent. I'm going to go to
So now I go Is everyone able to run the Numpy okay?
Yeah. You know, there's all these signs.
Yeah, you might not be fully up to date.
2 years. Some larger sample.
So I think you're running an older version of
Yeah.
So navigate to the So now
If it's the clone, we should have like the assignments for
so yeah, this is actually my fault. Well, what you can do.
That's fine. So go to like directly that you want to save.
The problem is that you have some different version of that file than variable. So some people have a problem too.
Yeah. So okay, so now you want to go to the website, and you want to go to this and let's see. I don't know if that's the right. Yeah.
Quite a stretch.
Yeah. So then now we have like clones. Periodic levels
So it's just merging basically the remote changes that I made, so I can have locally those. Okay. So I wanna work through loading a sample. Hey guys, if I could have your attention. I want to work through a sample data set. If you read through the IPython notebook, you'll see that there's a combination of text and code. Scroll down to the first exploratory data analysis. We're going to be working through examples of data from the UCI data set. UCI, the University of California, Irvine, has a bunch of machine learning data sets that we can work with and use. You'll see these used a lot in various articles and various publications. So these are commonly used data sets, and we're going to work with one today that's related to actual real-world data on heart disease, and actual medical information regarding heart disease. Remember last class, we talked about the formats of data. And the data that we work with in the UCI machine learning repository will typically be in a tabular format. In other words, this is very much like reading a table in a database, very much like representing a spreadsheet. When we're looking at data, typically we can represent it where we have a certain number of columns. We represent it as a matrix, basically. And we have a certain number of columns. So let's say we're looking at an example would be survey data. And we had one column for someone's age. We had, say, another column for person's height. We call these attributes. Throughout the class, we'll call these columns of data, these attributes. We'll be consistent in calling these attributes. Height, maybe have weight, and so forth. So familiar to all of you, you've all dealt with data in this way, in some way or another, be it in high school, whatever, in your everyday work, working with Excel, if you're working with SQL, working with databases. This is a familiar format. And so this will number these rows with numbers like so. So person 0 has an age of 64. They have a height of, say, 170 centimeters. Sorry, yeah, height of 170 centimeters, and they have a weight of 72 kilograms. Person in index 1 has an age of, I don't know, 31. This is generic data. I mean, this can be anything. We can be talking about cats, we can be talking about dogs, we can be talking about automobiles. It has a height of 154 centimeters. And they have a weight of 69 kilograms. We call each of these rows. So a column in the cell gives us a list of attributes for a particular, so columns are attributes. We call these rows, in statistics, we call these rows observations. Each one of these would be, if we were to plot it on a graph, each one of these rows would be a data point on that graph. So let's say we're taking a survey of this data and we have, so this is row, maybe we take 1,000 samples, right? So the last one here is 999. 999 because we started at 0, so it's 1,000 observations. We denote n, the number of observations, as n. The number of observations is n. The number of attributes, the number of features, we'll call this n. Let's say the purpose of this survey was to find people who had cancer. So maybe I'll add, just sort of make this relevant, I'll add whether or not they were a smoker. And we could represent this as true or false. I'm going to represent it as 0 and 1. Rather than representing it as true or false. The reason why I use 0 and 1 rather than true or false is because it makes my data types consistent. 0 and 1 is a numeric attribute. If, let's say, if I want to say the percentage of smokers, couldn't I average this column? If I took the average of this column, what would I get? I would get 2 divided by 4, which is 50%. I would get 2 divided by 4, which is 0.5, 50%. So when I keep my attributes numerical, it helps the math a little bit. Because I can perform the same operations, I can perform the same, if I did the sum of this column, then I would get 2, the number of smokers. And that's why oftentimes it's better to use 0 or 1 versus true or false, because it makes certain calculations like averages simpler. And it also keeps the data type of our columns the same. These are all numeric columns. And on that point, I should probably erase the centimeters here. Keep it consistent. And just so I remember, I'll call this kilograms, I'll call this centimeters. Again, if I did a type, if I queried the type of all of these, maybe it would be a floating point. Depending on how the data was recorded, it might be an integer. If I was very precise, and everyone who was recording this data was very precise, then it might. Each one of these are continuous values, so they're best represented as floating point numbers or decimals. In this lesson, we're going to be working through a very, very similar example in Pandas. By the way, one more thing I want to get to before I continue is that let's say we were using this data to make a prediction based on these values of whether or not they had cancer. I might have an additional out of room to write. I might have an additional column vector, call this a column, on whether or not they have cancer. And so maybe this person's clean, this person's clean, this person's clean. This smoker is very unfortunate and has cancer. Because the point of this data, what we're trying to solve, is related to answering a question of how do these attributes correlate with cancer, we'll call this cancer our target variable.
The target variable is the same as dependent variable.
Not necessarily. You can have dependent variables that are not target variables. In a large data set, and the one that we talked about, that's a very good question. Target variables should always be independent variables. If our data is represented correctly, our target variables should be dependent on the inputs, what we call the attributes, the input data of our system. But just because a variable is an independent variable, a dependent variable, does not mean that it's necessarily a target variable.
So is the target variable one that we're trying to predict, or?
The target variable is one that we're trying to predict, exactly. That's why we call it the target variable.
So target variable is specific for a one analysis versus dependent and independent may not be used.
Yes, in general, there may be cases where we're looking at where we have multiple target variables. Like if we're talking about classification, right? If we were trying to, maybe you could think of an example, you could sort of extrapolate this example where we're trying to predict the type of cancer. Then we would have multiple dependent variables. So it's not necessarily one. They're all relevant, they're all target variables, but in this case we've sort of split it across types of cancer. So let's see how this would work in Python. Like, what would the process of this be? You have in this IPython notebook a link to part of the UCI machine learning data set. By the way, this is all public data. If you go to archive, and this is in the resources directory that I showed at the beginning of class. I believe if you go to UCI machine learning databases, it'll give you a list of all of these, and it's very unstructured, I guess. But there's a massive data set, and you'll see these used in all sorts of literature. The one that we're looking at is the heart disease. So there's one in here called heart disease. I'll paste this link in Slack. And what we have here, there's one of these in particular. So these are all different data sets related to heart disease, and they all have pretty much the same format. If we look at heart disease, you should all be able to click this link, the heartdisease.names. This file with the .names extension is a description of the data. Typically, in most data sets, particularly those that are published, it's very important that there is a description, that there is documentation on the data set. If I just gave you a table of numbers, if I erased all of these, and I just gave you a table of numbers, it would be pretty useless. So typically published data sets come with some sort of documentation, annotation. This particular heartdisease.names file contains a list of all of the, basically a descriptive list of what's being tracked in this data set. So if I go back here, I can look at Long Beach, Virginia, I can look at Hungarian data, I can look at Cleveland data. In our particular example, we'll be looking at process.cleveland data. So click on this, I'll open it in a new tab. Oops. Let me know, give me a heads up if my text is too small or if you can't read it. this is what I mean when it's very important to document your data. If I just gave you this set of data, it would be kind of useless. And sort of an obvious question, but is this structured or unstructured data? Yeah, it's very clearly structured. I mean, you can almost take a ruler and draw vertical lines. So each one of these numbers, again, each one of these, this is what we'll call a matrix, right? It's clearly two-dimensional. Each one of the values here is kind of like, each one of the columns in this data set is kind of like the columns I have here.
How many dimensions is it?
Two. And again, if we look through this, and I won't bore you with every single line of this description file. The attribute information, in my opinion, this isn't that clear, but it says this is all of the data that was collected. And here it says there's only 14 attributes used. That's age, sex, CP, which I think is, there's annotations here. So CP is chest pain type. 10 is, I think, blood pressure. So all of these are basically described here. What's important though is that each one of these, see how there's 14 attributes here? That's the column of this, what we'll call this matrix. So if I look at the leftmost column, I see 63.0. If I look back here, that's the age. So this person, each one of these rows is a person. This is a person. This is a person. This is a person. This first person, maybe I should say 0th person, is 63.0 years old. Again, this is being represented as a decimal. He's probably not 63.0. This guy's probably not 67.0. It's just the way that the data was collected. This would maybe be a point of optimization, but the way the data was collected, it was only looking at the exact, or the integer year. Here we have, the second field is sex, gender. Again, notice how this is a numeric attribute. I don't know if gender should be a numeric attribute, but in this case it is. They're keeping all of the data types consistent between each of the rows.
I have a question.
Yeah.
So all of the data sets there, it ends in point 0.
Mm-hmm.
Is it, when you want to try to make a structured data, is it important to just keep it consistent the way you are using certain data for, like, does that make sense?
Yes. The answer is you can convert an integer to a decimal without any loss of precision, right? But you can't convert a floating point to an integer necessarily without loss of precision. If the data that's given to you is in a floating point format, it's probably, or a decimal format, it's probably best that you keep it in that format. Because all of the operations that are valid on integers are also, like division, etc., are also valid on floating point numbers. So I would not risk the loss of information by converting it to an integer, even if it's clearly a sort of a binary attribute. The reason is, this is something that we went over briefly last class, but if I'm say taking an average, right, and I say my first person is female, we'll say 1 is female, we'll say 0 is male. If my first person is male, my first person is female, my second person is male, my third person is female, and I want to average this, what am I going to get as the result? I'm going to get 0. If I keep it in a floating point format, now what am I going to get? Yeah, 0.666. So this is why it's useful to keep it in the format. This is why it's in the floating point format to begin with, which is why I mentioned here. My average here, the data set, there's 2/3, 66.66% of my data set is female. So even though, yes, there's sort of an arbitrary assignment of floating point values to what's really a binary attribute, it does make certain calculations easy. And so this is why, for reasons like this, it's sometimes better to keep it in a floating point format. The drawback with that is that floating point numbers are little bit larger. They take up more space. There can be rounding error in some cases. So it's not always, don't always use floating point numbers, but in general, it's better to do mathematics and calculations on floating point numbers than it is to do it on integer numbers because you don't have to worry about, truncation. Almost all languages almost always round down. It's not specific to Python. That's the documented behavior. So C, Java, most languages will basically do, it's not actually rounding down, it's technically doing truncation. So what it's doing basically is it's saying an integer divided by an integer is an integer. That's sort of the rule it's applying. It tries to keep types the same. So if I say cast a particular value to an int, and I say 4.3, then it's going to truncate that. It's going to basically say, I'm going to take more information and convert it to less information. This is what I mean that when we convert from floating point to integers, there's usually a loss of information, in this case the 0.3 at the end. But to answer your question, yes, most programming languages will truncate.
Just one further question. So in the example you just gave, you converted all of the genders to float.
Mm-hmm.
Now, if one of those genders was an int, would that change the behavior of the somewhat change the nature of the calculation? Or more specifically, they had 1,000 elements, and only one was somehow that corrupted as an int or cast as an int.
If I add a floating point number to an integer, what do I get? Yeah. So if I do, so think of it like this. If I have an integer plus the floating point, this will give me a floating point, right? With me so far? Yeah. If I do a floating point divided by an integer, what will I get? Floating point. So if I do an integer plus a floating point divided by an integer, isn't this the same thing as the float divided by the integer? So the answer is it'll still give me a floating point. So if I did this, and just in practice, if I did this and I say, converted this to an integer, then it'll give me the same result. That's why it's very important. This is why what I talked about at the beginning of class, at the beginning of the course, was paying attention to types. It's very important that you pay attention to types because stuff like this, subtle differences, like whether or not you're dividing by an integer, whether or not you're doing operations on floating points or integers, does matter. And it can manifest bugs in unexpected ways. So it's just very good to be in the habit of always thinking and paying attention to what your types are of the variables that you're calculating on. Okay, cool. So we have a matrix of data, and we have again a list of names that correspond to, that map to the columns of data that I've shown to you here. I'll sort of put this aside so you can sort of see in parallel. Going back to our IPython notebook, going back to this practice information, this was just cut and pasted directly from that description file I showed you. So I mentioned that we can evaluate things in line. We can evaluate code directly within IPython, and the way we do that is we can say create cells. So each one of these pieces of information in IPython is called a cell. The first one here. So this is just code, just like I would have in any other editor. If I can modify it like so. By the way, I can double click. If I want to edit, I have to double click that cell. This is all Markdown. We talked briefly about Markdown, the format of Markdown, but it does, all the formatting here is defined as being Markdown. And so when if I click Control Enter, it will evaluate that cell. And so it's evaluating the markdown that it's rendering here. Similarly here, and this code is already sort of half cooked, but if I hold Control and click Enter, it'll evaluate that cell. And the number here gives the order of evaluation. So even though it says this is the third cell, so if I run all, oops, I'll scroll up. If I scroll, I'll see how the number, I have, I think, 16 or 17 number of these cells. So when each time I run it, it's going to increase in number because it's technically, rerunning that cell. It's sort of starting over. But I'm just going to basically print, just to sort of show you that I can edit these in line. I'm going to print each of these outputs. So I can run this cell again. Oops. And when this prints, it prints out the values of the list that I created in the previous step. So IPython is called interactive Python. It's called interactive Python for this reason because I can interact with it and I can do things. I can describe what I'm doing and document what I'm doing within the code itself. What I've done, I'll sort of run through these each one at a time. This initial line here is basically just giving a style sheet. That's just for code highlighting. It's just what gives me this sort of, it's linking a style sheet to those of you who have done HTML are familiar with this. It's just linking a CSS file, the hyrule.css file, which just defines the styles for colorizing the code. It just makes the code look neat. So when I do import pandas as PD, when I do import numpy as NP, the nice, fancy, bold, whatever is displayed through that style sheet. We're using, in this particular exercise, we're using two modules that are really core to the lesson. That's Pandas and Numpy, and they complement each other. Numpy, they're similar in a lot of ways. So, last few lectures, we talked about basically just Python. In other words, Python has this, I guess, what we call the core Python stuff that you can do within Python without needing to import external libraries. When I use this import command, it means that I'm importing a library outside of Python, outside of core Python into Python. There's also the standard library. Virtually all languages have a standard library of common tools. So this would include, core Python includes things like we talked about dictionaries, lists, and all of the basic data types that I interact with regularly are part of core Python. I don't need to import anything to use dictionaries. I don't need to import anything to use lists. I don't need to import anything to use integers. Those are just fundamental data types that are defined in the language without importing anything. Then there's the standard library. That is, when I download Python, it comes with a common set of tools, of modules, that are very commonly used, that come with the language, sort of, it comes pre-assembled, but aren't imported by default when I run Python. For instance, this includes regular expressions, which we covered last time. Regular expressions, if I want to use regular expressions within Python, I have to do import RE, which is the module for regular expressions. There's a bunch of other stuff like operating system specific tools, system specific tools, we talked about JSON last time. So there's all sorts of stuff that's commonly used, but it's not stuff you're going to be using likely every time you use Python. And this is what we call the standard library. What Pandas and Numpy and the other tools like scikit-learn and even IPython, these are external community tools. So within community Python, is basically community, open source, often open source. Open source projects. And these are often installed with pip. There are sometimes pip/conda here. They're usually hosted on GitHub. They're not installed by default, but they are installed with Anaconda. So Anaconda, what Anaconda is, it's a bundle of all of these commonly used open source tools. Not installed with Python, but Anaconda comes prepackaged with several of these modules. So in other words, the tools that we're using today in class, the tools that we're using throughout the class, were not actually created by the Python core developers. They were created by the community. People like you and I who found interesting problems to solve and built stuff on GitHub and now have a very popular and very commonly used framework for doing data analysis, machine learning, etc. And the two we'll be covering today are called Pandas and Numpy. One thing a few people of you asked is, what does it mean, the import statement? What does the import statement mean? By the way, whenever we call import, we're importing what's called a module. We're importing basically a suite, a collection of tools, of classes, functions, sometimes variables that we use, that we introduce to our Python environment. So when we call import pandas, when we call import numpy, we're actually introducing additional capabilities of Python. When I say import pandas as PD, it's actually, the way it works is, the way Python does it, and the way this is done in your operating system, the way this is done in every language. And I just want to at least just a quick tangent and show you how Python tracks modules and how Python searches for tools. In every operating system, whether you're on Windows or Mac, you have a thing called your path variable. And I don't know the command to show it in Windows, but the path variable is a collection of folders. It's just a collection of folders in my operating system that my operating system does to look up when I issue commands. So when I say Python, or if I say anything else that's accessible at the command line, even cd, even ls, those are programs that I'm running in the terminal. When I say Python, I'm actually running a program. The way my operating system finds this program is by looking through each folder in the path. And this is not just for Python, this is for Git. This is for anything that I type here that can run. When I say Chrome, all of this stuff is stuff that's loaded from my path environment. If I look closely here, and maybe this isn't the best way to visualize it, but this is just a list of folders, isn't it? If I look at the first one, I see users, Erlanger, RVM, Ruby-2.1.5. That's my Ruby. That's how for the Ruby programming language, that's how I load Ruby environments. But if I look at the next sort of collection of folders, I see something called PyEnv, and I use a tool called PyEnv to manage my Python environment. But looking further, you can see there's all sorts of stuff in here that my operating system is using to look up where files are. If I look down here at the bottom, there's one called users Erlanger anaconda/bin. Again, it's just a folder, but because it's in my path variable, it's one of the folders that my operating system looks up by default. So if I navigate to that folder, what do I get? I get a bunch of stuff here. But if I look closely, I'll close out of this temporarily. If I look closely, these are all stuff that's available to me within my operating system. And one of them is called Python. I also have Python too. But if I run this, and if I use // that means I'm running a file from within the local repository, which in this case is anaconda/bin. If I do /python, I'm just running a local program. Again, I can run this. I don't need to navigate and call. I don't need to. I can run this anywhere within my local environment. So right now I'm within my home directory, and if I run Python, again, I can run Python because it's within my path variable. Now, a very useful command on Unix is the which command. I don't think that this is available on any Windows machines, but if I do which/all Python, it's going to say which file is running when I type Python. And I get 3 values. The first one here is my default Python. This is actually the one that I use on a day-to-day basis, which is managed through a virtual environment. The second one, user bin Python, is the one that was installed with my computer. The last one here is the one that I just showed you. Again, it's within this anaconda/bin/python. So if you're ever wondering where or which particular program is running when you run a command at the command line, use the which command. It's very, very useful. Now, this is a standard. This isn't just something that's specific to Unix. This isn't something that's specific to Windows uses this, Unix uses this. But interestingly enough, Python uses this sort of system of looking at modules as well. So the modules that I use within Python, whether they're standard library modules or whether they're the open source community Python modules, Python has its own path-like variable, a list of directories that it uses to find modules that I can import into the operating system. So when I type import pandas, there's actually a path-like variable that Python is looking up to say, okay, well I know what pandas is. If I just use the base Python installation that came with my computer, I would not be able to import pandas because pandas, again, is not part of the standard library. It's not part of core Python. So there's no way for Python to know what pandas is unless it has a bunch of folders, an environment with which it can find modules I can add to Python to look up, such as community modules. You should all be able to follow along with this as I go, by the way. If I do import sys, I can see what specific folders Python is using by looking at sys.path. This looks sort of similar to what I just showed you in the path environment. This is just a list of folders. Again, the first one here is an empty string, which means my current working directory, where Python was loaded from, which in my case is my home directory. I just loaded this from, again, the tilde just means my home directory, which is the same as your home directory that shows up in the Finder in Mac. In Windows, I think it's My Documents. There's a bunch of folders here that Python uses to look up where packages are. So there's setup tools, there's PyM version, there's stats models. Some of these are all just a bunch of tools that I've sort of added myself. And so as long as the Python code, the module I want to load from, is within this list of directories, it can import pandas.
Anything like which to see what specific packages?
That's a good question. Not off the top of my head, but I wouldn't be surprised if there is one. I don't know off the top of my head, but yeah. Yeah, I don't think so that I know of, but I'll figure that out. So, sort of coming back to NumPy and Pandas. We can basically, I want to basically do this within a new notebook. To sort of show you guys how to create and work with a notebook. If I go back to the directory I used to load IPython from, if you click this new notebook button, I can start a new notebook. And I recommend to you guys when learning this stuff, as we go along with this stuff in class, just cut and paste. You can cut and paste the stuff directly from one cell to another. So just to sort of include the HTML, I'll run this. And again, when I press Control-Enter, it'll run that cell. If I do Alt-Enter, it'll run the cell and it will also create a new cell below it. And maybe it's a little bit too large, but I can interact with these cells. Just basically I can edit text in them. But when I create a new cell, it's basically running them in sequence. So if I do A equals 5, and I do Alt-Enter to create a new cell below, and I say B equals 7, and then I do print A plus B, then again, it's going to maintain the history. So if I say come backwards in time, and let's say I think, oh, well, I want to rename this C, and I run all of the cells now. If I press play to run all of them, or sorry, press play to run each one, it still remembers what A is. So A is still technically in scope. So be careful, because I never actually removed A. When you go backwards and you edit history in IPython, you can sometimes get undesired effects. Similarly, if I do print C plus B, then this will also work. So I've actually I've left some garbage in my history that I'm still not currently maintaining. And that's often a confusing point of IPython, is that sometimes, even though, like if I were to look at this code, when I run this once, because it's still in memory in a way, A is still in memory, I can still run through it. But if I were looking through this, I would say this is going to be an error. What's A? This is going to be an error. What's A? So if I ever restarted this notebook and ran it from scratch, it would basically fail. And so sometimes it's sort of criticism, or sometimes point of issue with IPython is that you can have something that runs in a local session, but let's say if I gave you this source code, then it would fail for any of you in this class. If any of you were to run it from scratch, it would fail because it doesn't know what A is. It doesn't know what that is, because it's not going to be in memory for you.
Keep stuff in local memory for too long.
It's not. I would be in the habit of restarting your always making sure that your notebook can run from scratch. So there's actually a option to do that under kernel restart, and it'll give you this warning. It'll actually say all variables defined in it, which in my case is okay because I have sort of a stray variable defined. But if I restart, and then if I rerun this, it'll give me that error, name error. day is not defined. So just something to keep in mind, just a caveat. You know, if you're up late one night and something's working and then the next day it's not working, it might be because, you know, you had something that was stored in your environment that was not that was stale, basically. Okay. Getting that out of the way, let's sort of go through this one by one. I'll go through this really quickly, but you're going to see this pattern a lot. Import pandas as PD and import numpy as NP. In other words, pandas is a community module that we're importing it, and we're aliasing it as PD. We're naming it PD. So, you know, oftentimes you see this pattern in Python, import X as Y, and it's kind of confusing because we're basically just saying, I want to call pandas PD, so I'm not confusing it with you know, if I wanted to say declare a variable named pandas somewhere else, I have the option to do so. Same thing with numpy. So this is what's called an alias. And you see it a lot in programming where you alias a variable because you don't want to, if it's a commonly used name or if I want to, you know, reference it as something else, then I can do so using an alias. But I should be able to run this just fine, and I can, no error. I can also delete cells. So for those of you who have used Vim, the commands in IPython are sort of similar to Vim. But just for your reference, you can view, I think it's H to view to view documentation. You can do IPython help here in the help menu. The IPython hotkeys, user keyboard shortcuts. You should know all of these. You should go through each one of these keyboard shortcuts, and some of them are more important than others, but understand the difference between command mode and edit mode. You can double click a cell, so for instance, you can interact with IPython you know, when you're not editing code, and that's called command mode. When I double click on a cell or when I press enter on a cell, then I'm in edit mode. And so, you know, all of this stuff like tab, etc., will have different operations in command mode and edit mode. One of the great things about IPython that's not available by default in the default Python console is tab completion. So remember I said import pandas as PD, import numpy as NP. If I do PD dot and do tab, I can see all of the stuff that's available to me within the PD module, the pandas module. There's a lot of stuff here, and this is again one of those things where, you know, 95% of this stuff, you'll use 5% of it 95% of the time. And we'll cover a little bit of that today, but we'll be covering it also throughout the class. What's really cool though, and this is a part of Pandas, is that I can put a question mark at the end, and it will basically give me the documentation, it'll give me the help on that particular class or function that precedes the question mark. So if you're ever in doubt, if you ever want to look something up quickly, put a question mark at the end, and I just evaluated this cell, so the last thing evaluated is what gets sort of, you know, executed. But it gives me this very useful help documentation. So I can see, you know, the description, all the parameters it takes. So this is something you'll be using a lot, is this question mark syntax at the end. It comes from the source code. It actually comes directly from the source code. In other words, if you look here, it's looking. There's this thing called a doc string. Doc string is short for documentation string, but a common pattern in Python is where you have basically a block of string, a block of text that acts as the documentation for a particular function call or class. And you can embed that documentation directly in the source code so that in environments like IPython, I can pull that up and I can, you know, view and review that information. And it's just a convention that's extremely useful in Python. I can also, if very similar to the question mark, I can do Shift Tab, and I can get the very similar documentation as a pop-up. So this tells me the arguments that this is actually a type of function called a constructor. This tells me the arguments that the data frame constructor takes, and I can expand that, and I actually see the same sort of, notice how this is the same information that the documentation. So it's an alternate way of getting the documentation, which is shown through the question mark syntax. On a similar note, if I do 2 question marks, I can actually see the direct source code itself. So now, remember I talked to you what the docstring is. 3 quotation marks in Python gives me what's called a block string. So it's a multi-line string, and I can just type in that in freeform. But if I keep scrolling, and I keep scrolling, and I keep scrolling, I'm actually seeing the source code here, right? So once the docstring here, make this larger. The docstring here, this is again the actual code. So I have this is the source code class data frame, and it opens with this docstring that's nested directly under the class declaration. And again, a lot of this stuff, this is Pandas is a more advanced Python library, so a lot of the stuff in the source code is outside the scope of this class. But I find it extremely useful to be able to check and cross-reference the source code, and I do it quite often. And I recommend that, this is a great way to learn, is to, read other people's code, especially code that we're using in this class, because it'll expand your knowledge of Python, and it'll make you a better programmer, and it will also increase your familiarity with the tools we're using in this class. So again, you see all this stuff in the documentation. This is kind of like Markdown, isn't it? It's not quite Markdown, but you can see that the formatting for the text is embedded within the text itself, which is the value of Markdown. And most documentation styles have a similar sort of paradigm. So we have examples, we have the parameters that it uses, we have a general explanation and the description of the data frame. And all of the stuff that would be very important to have in documentation. The underscore init is the constructor, and so again, now I'm looking at the actual source code, and we won't obviously go through all this. There's quite a bit of source code in this file, but just so you know, you can always at any time look at the source code by doing 2 question marks. By the way, now that I have a bunch of old cells in my environment, and I talked about how IPython sort of follows Vim, I can press D. If I'm in command mode, I can select, my each one, and if I disable, I have speaking of Vim, I have a plugin that emulates Vim within the browser, so I have to disable it and reload the page. But if you press D twice on each of these, then it will delete that cell. Since I'm using a plugin that's overriding my default tools, I'll do it from the edit menu. So edit, delete cell, edit, delete cell. You can press D twice and it'll do the same thing. So now we've cleaned things up a little bit. So I want to give you guys an opportunity to sort of play around with this and familiarize yourself with the IPython notebook. There is a very simple, and this is where under practice, there is a very simple demonstration that sort of goes through what we talked about, over the last 45 minutes or so, and actually loads. It goes through using pandas to load the data set. So again, pandas is a tool that allows us to represent and summarize data in a tabular form. But before we need, and the data that we're getting from from the UCI data set fits that form. What we're solving in this particular exercise is getting data from the internet in this tabular format from the internet, and we're putting it into, we're loading it into Python. So you should all be able to run this, but rather than just run it and not learning anything from it, actually put comments. So I can comment a line and actually add your own sort of description of what you think each line is doing in your own words. So we'll give that 10 minutes, and then we'll go through it quickly, and then we'll go to break.
And around,
I'm sorry?
starting from where?
Just after the code that starts just after practice, reading, and data. So if you scroll down below practice, reading, and data, you'll see a code snippet that begins with the line header underscore row. And play around with that. Try to break it. Try to do interesting stuff with it. But most of all, just insert your own comments in your own words that represents what you think each line is doing, and then we'll go through it together. So we'll reconvene at 8:25. By the way, IPython by default doesn't give you output, so if you want to see what's going on, it might be useful for you to give a print statement before each. If you want to actually echo what's going on to see the evaluation of each individual line, just put a print statement in front so that when you run the evaluation, it'll give you some output here. Sorry, output here. Do the same thing with URL. If I do print URL, it'll then give me this, and then it'll give me the URL as well.
No, that's specifically checking enough. When you first load this,
Zero to that. That's what we're
Yeah, that's really good.
I'm just in like the lecture 4. 0.02. I'm just wondering which iPython I'm over.
Yeah, I'm not sure for stats with Pandas, and then you'll take
It's under the
Yeah, that's what I have.
I think it actually is.
They're not full.
Everything working okay? You're using older version file for the header. So when I updated the repository last week, I posted on this in Slack. So if you follow the instructions in Slack,
Yeah, I did that. I remember you posted some like mad like this. Yeah, I did.
yeah, try running again. But that'll do any updates or any changes you have to the local site or stuff like that.
Yeah. Why was it unrated?
Yeah, he made some changes.
So now we can index the profile. So in this case, see that we actually pass or yeah, so this is just reading it. This was that's the header. Then you do uses. So this is that if you have some CSV to add a header on the book, you can cross out. You can also if you turn it on pass info arrows here, we actually set that. Yeah, I mean, so I mean, right now it's saying unique identifiers as well, and then the modifiers. So it's saying each row is one out. Here, copy and paste everything you just saved, exactly what it does. Follow the logic.
You have that discussion, right? So we do that.
Right. Otherwise, all the information is just import the file.
You just have a bunch of information.
I think we see is also view the whole thing.
If you want some, like, a wall marker.
Usually it's taxed about like 6:30 or like 6:35.
I was
All right, so let's go through this really quickly. So where did the header row come from? Yeah, we created basically to match really the description of data given provided by the UCI dataset. Right, so there's 14 total attributes. So we're using basically we're just declaring them one after one here. But when I run each of these, really what I'm doing, if I can find the file. Basically what we're doing is we're basically loading, so we have a header row, we have a URL, and we have the actual data. So really where all of the heavy lifting is being done is in the read CSV file, the read CSV function. And so we're reading basically directly from this URL. What's important though is that this URL has a very consistent format, this process.cleveland.data. So because this is in a very consistent and regular format, Pandas is able to read from it. This style of format is sometimes called comma-separated values, where each value, each attribute for each observation is separated by a comma. So we have a matrix. We have a matrix of values here. That's a good question. So Pandas is actually very good at finding patterns in data, and I believe it will work if you do semicolons, and it will work if you do spaces. It will work if you do tabs. And that's one of the strengths of Pandas is that we can do that without, it's very flexible in dealing with various data formats. So if I were to go, if this were say provided with tabs or with semicolons, then it would find those patterns.
Are you saying if you call it the read CSV function, it'll still figure out the separator is or it's not?
It will for tabs, yes.
Oh, wow.
I'm pretty sure it will for semicolons. I'm not 100% sure for semicolons, but
So you can pass the delimiter explicitly.
yes. Otherwise, you have to pass. If it's tabs or commas, then you can do it automatically. Otherwise, there is an argument. And remember, yeah, if I put, for instance, if I do the pd.readcsv, then let's say, I want to sort of answer that question on my own. There is a parameter in here called sep, delimiter to use. If sep is none, we'll try to automatically determine this. Regular expressions are accepted. So, yes, what's great about Pandas is that it has this automatic behavior. And, Pandas, there's been a lot of things that I've been able to load fine in Pandas that I can't even load in Excel, that I can't load in Ruby. So Pandas is very, very good at finding those patterns in that data. But if you have a problem, you can override. So let's say if we wanted to, in this example, if we wanted to load this based on decimals or periods, then you can imagine we'd have a very different result. So you can actually modify this. But yeah, in general, Pandas is smart about extracting that information. Other questions? By the way, how would we talked about representing collections of data in Python. How would we represent this? If we wanted to say represent this in plain Python, how would we do it? Exactly, it's a list of lists. In fact, it's not just a list of lists, it's a list of lists where each of the lists, the inner lists, are all the same length. In other words, it's a matrix. I'm going to switch to, well, I guess I'll do it in one environment, but I want to sort of show you how Pandas represents that information. So when we run read CSV, and when we print heart data.head, maybe some of you got to this line. What head does is it basically gives us the first, I think, 15 rows, or first, I think, 10 rows of that. It's a good way of previewing our data. Remember we talked about the length function? Heart data acts kind of like a list. In fact, it is a list of lists. So, a list of lists behaves just like a list. If I print the length of heart data, remember I can print, this is a list. If I make a simple list, so 1, 2, 3, 4, and I say the length, if I want to know the length of that list, remember we can find the length of a list. And I'll run this cell. What I get is 4. Obviously, this is a list of length 4. But notice how heart data acts like a list. It's giving me 302. In other words, I'm not going to count them out for you, but there's 302 rows, 300 sublists in this list. So I can. What do you think I'll get if I do, say, this? Well, I can't quite access it. It doesn't quite act like a list. But
Why? Because there's no comment yet.
well, because there's no comment at the end of the this.
No, when you put in that bracket 0, and yeah, if you put a okay, sorry. No.
I think, if I recall correctly, Pandas, depending on the version of Pandas, sometimes it will output this. In other words, it'll treat it as a list. But really, I mentioned Numpy, and I guess I sort of skipped over Numpy. But what this is, if I were to just basically look at what the data is here, this here is what we call an array. Sorry, I'll call it an array of arrays. It's represented in memory as an array of arrays. Arrays are a native type to Python. By the way, sometimes I'll use arrays interchangeably with lists, because I'm used to calling them arrays on a day-to-day basis. Unfortunately, a lot of names in Python don't have the same names in other languages, but arrays are lists. Sometimes they're called vectors. In R, for instance, they're typically called vectors, although R also has lists. But I'll use the word array and list interchangeably. So this is actually a list of lists, an array of arrays. In fact, they're all the same size, so we'll call this basically a matrix. The way this is represented internally, Pandas is actually using a module called Numpy. So if I look at heart data, and I want to just look at, I just want to look at heart data, I can call .values on it. .values is just this array. And so again, I get a very large result, and it gets truncated here, which is a fortunate thing because I wouldn't want to flood my entire window with 302 rows of data. But each one of these is, again, this is very similar. I could conceivably, assuming I didn't have the ellipsis, I could basically just almost cut and paste this result into Python. If I got rid of all of these ellipses, then it would be a valid matrix. But the question for you guys, what do you think the type of this is?
Type array.
Well, it actually isn't. Well, you're close. And yes, it is kind of an array. It acts like an array, but it's not actually an array. What I get is numpy.nd array. And I talked about both, we have NumPy, and we won't be interfacing with NumPy as much in this class, But what NumPy does is NumPy handles storing data in really matrix type format. Does it numerical analysis? So the internal representation, the internal storage of data is handled by NumPy. NumPy is really wrapping the native implementation of lists in Python. And Pandas is itself wrapping NumPy. So, if I find where I put my rag, really, again, we talked about Community Python, and we talked about Pandas. Pandas and NumPy are both community modules. So, in Python, we have the list type. And NumPy, the creators of NumPy came around and said, hey, lists are really valuable, they're interesting, but what happens when we want to do operations on, what happens when we want to do multiplying matrices, what happens when we want to deal with matrices or deal with things like dealing with data on a larger scale. So they took lists, and they basically put them on steroids, and they created a package called NumPy. And NumPy is inspired largely by the syntax of MATLAB. NumPy obviously means numeric Python, inspired by MATLAB. MATLAB is both a programming language and an environment also for dealing with what's called numerical analysis, dealing with calculations, computations on large data sets. It's used often in the data science community. Some of you may have worked with it. MATLAB stands for Matrix Laboratory. Keyword here being matrix. So NumPy handles things like numerical, what we call numerical analysis, which is the field of computing which is concerned with solving equations, simulating things, doing all sorts of stuff that's not just related to data science, but that's related to engineering as well. If I want to simulate the circuit, the current in a matrix, if I want to simulate the physics of a system, oftentimes those systems are represented by complex equations, and those complex equations are represented by matrices. So I'll call basically solving systems, solving and representing systems of equations. And what I mean by that is this is often what we call the branch of mathematics called linear algebra, which we'll cover a little bit in this class, but we won't go into too much depth. Linear algebra. In other words, basically matrix and vector operations. So that's what NumPy does. NumPy is low level, it's nitty gritty. It does things, it's optimized to do quick calculations, it's optimized to do things that would normally take Python or high level languages. It's programmed at low level with C to make these sorts of common numerical analysis operations very, very fast. It's very, very sleek, it's very, very lean. And on top of NumPy, there's Pandas. Try to, I'll write it over here. I'll write a big arrow to basically show NumPy extends, Pandas extends NumPy. So Pandas is a tool for representing representing and performing calculations on tabular data. And what are those tabular data? We call those data frames. And it turns out that Pandas is a pretty big library. It also handles things like plotting. It has a lot of statistical tools. I don't know if you guys can see okay. Statistics, and also analysis as well. So anything again, Pandas is internally representing this sort of green triangle as an ND array, a Python ND array. Sorry, a NumPy ND array. And NumPy itself is using Python lists. This purple part, again, this purple part, Pandas almost literally wraps this data frame in what are called indices, the columns and row numbers that make up our data. And we call this a data frame. Yeah.
I get the sort of literal, high-level explanation of each and what they do. Would it be possible for you to give us a quick and dirty example of kind of how you go through a business problem or a research objective, and like maybe just how you would kind of use both? I don't see how these things sort of complement each other just conceptually.
So the reason why they complement each other is NumPy does what it does best, which is storing information, storing data at a low level. So Pandas is less concerned, because Pandas extends from NumPy, it lets NumPy handle all the heavy lifting of how to do calculations on data. NumPy was built to be fast, it was built to be lean, and so from the perspective of the developers who wrote Pandas, there isn't really a need to reinvent the wheel on how to represent data. Because when you're talking about doing calculations quickly, like let's say I want to perform an average, or let's say I want to do basic statistical analysis. NumPy, because it was written in C, most of it was written in C, and it has this sort of wrapper, which is in Python, it's very, very fast at doing those calculations. And there's a lot, for all the stuff that Pandas does, Pandas is really just sort of an interface in a way to interact with NumPy. All of the stuff that Pandas is doing at a low level is being done by NumPy. So if I said average a column, like I want to find the average age, what Pandas is doing is Pandas is basically calling sum on a vector. I'll give you an example sort of in the console, right? So if I create a new cell, I have here, again, I declared this data frame here called heart data. And within heart data, I can reference, remember we talked about dictionaries? Data frames act like dictionaries. So if I do age, I have a column called age. And again, if I print that, it looks familiar. So I'm basically just slicing. This is called the slice. I'm slicing one field of data. And if I do sum, the actual summation, this will give me 1,432. If I do, I think it's mean. The mean age is 54.41. And this is not this isn't a very difficult calculation, but you can imagine if I'm dealing with a real data set, and let's say I have 20 million of these, 20 million of these individuals, 20 million of these observations, and I want to do a mean. This mean is being calculated by Numpy. So in other words, the actual calculation itself is being done by Numpy, but the function call is on a Pandas object. So you can imagine that within Pandas, so I have data frame. Within data frame, there are a bunch of methods like, say, sum and mean. And if I were to look at the source code and the implementation, if I were to sort of, look at what the source code showed, I would actually see some numpy.sum divided by some numpy.length, something like this. So the data frame object is calling numpy internally in the source code. And I guess we don't have too much time to look at that in detail, but just to sort of show you, and again, going back to what the double question mark does. Oops. I won't have time to dig through the entire code, but if you were to look at the source code, you would see basically a bunch of NumPy calls being made within Pandas. Does that sort of answer your question?
Yeah, I think it is.
In terms of like the real world application of why it's important that Pandas uses NumPy is because it's very, very difficult to write those low-level operations, to write those. There's been a lot of people at a lot of different organizations that have written the tools that are used by NumPy because it's very difficult to program those matrix calculations. There's a lot of details involved in doing that numerical analysis, and this isn't something you would want to build from the ground up. If you're, say, trying to solve a problem where you were trying to find the average age of 10 million people, then that's not something you want to be doing in native Python. It's something you want to be doing in C. And so NumPy is a way of calling low-level functions, low-level C operations within a familiar and friendly Python environment that's just delegating to lower-level subroutines that are actually implemented in C.
So it's just essentially an efficient way of leveraging something that already existed.
Exactly.
Yeah.
Exactly. And it gets very, very complicated. It gets, if we were to sort of like extend the conversation, NumPy is actually using a bunch of tools that are written in C called basic linear algebra support. And there's a bunch of tools, and these are often maintained and built by universities and PhD students at various universities, and some of them are written in Fortran, some of them are written in C, but there are a ton of them out there. And so NumPy just takes those C implementations and it wraps them in a familiar C interface that conforms to how we interact with lists and primitive objects in Python. What's also really useful about Pandas is that it itself conforms to the common interface that we see in dictionaries. If we look at I sort of mentioned this a few minutes ago, but we can call common operations we can call common operations that are common to lists on data frames because they are basically like a type of list. I talked about how a matrix can be represented as an array of arrays, right? If we sort of for a second take around the index, these attributes, the list of attributes and the list of row numbers are called in Pandas are called indexes. But I can numerically represent a data frame as being an array of arrays. But can I also think of it? Sort of if I extend that concept, can I also represent a data frame as a list of what? What else have we talked about? It's basically a list of dictionaries, right? It's a redundant. I can basically, if I take a slice of this values, I say just look at this particular observation, right? Again, I'm going to ignore the row index information, but I'm going to look at this. This is basically a key, this is a value. This is a key, this is a value. This is a key, this is a value. So if I just look at this row, it's just a dictionary. If I look at multiple rows, it's just a list of dictionaries. The reason why data frames are a little bit more convenient is because if I have a list of dictionaries and I have some repeated information because I'm repeating the keys each time. But in terms of representation, in terms of how it's represented, it's exactly the same. So we'll, this is not stuff that's specific to, this lecture. And I really want to stress this point that data frames are a fundamental data type. This is not something that's specific to this lecture. This is not something that's specific to this course. It's not something that's specific even to this lecture. Data frames are used everywhere. They're used in SQL tables. They're used in Excel. They're used in, it's a very familiar format. And so for those of you who have used R, you'll know these also as being, data frames are a common data type in R. They're a common data type in Julia, which is a new programming language. But this is something that we'll be dealing with data in this format. When we talk about structured data, the most common format for structured data is the data frame. And the reason why is because it's familiar, because the data frames act like lists, they act like dictionaries, and so it just extends the concept. It's a natural way of representing collections of data. So I want to make sure that you guys, one thing I want to cover at least, and then we'll go through sort of, we'll go through sort of the end of this as a class. You'll have a little bit of time to play around with this at the end of class. But what's great about data frames is that common operations on data frames are what we'll call reshaping and dealing with pieces of data in a data frame. So typically, if I have a full data frame, very often I'll want to look at a specific column, a specific attribute, a specific row. And we call this slicing. Sometimes it's also called subsetting data. And we'll elaborate, it's your, the exercises you go through, that we'll sort of go through in a few minutes. But we'll also build on next class, revolves around how to represent, how to reshape data, how to take pieces of data and sort of break it down into more manageable chunks. Or, basically sometimes you might want to discard data, sometimes you might want to, represent this tabular format in a more concise format. So I'll write a list of common data frame operations. So there's two forms, I guess. We'll talk about first. We'll talk about subsetting. Which is sometimes called slicing data. Maybe sometimes I want to look at a subset of my data. I only care about patients that have cancer. I only want to look at patients that are above a certain age. Or sometimes I only want to look at certain attributes. I don't care about a patient's height. Maybe I don't care about a patient's weight. Maybe I only care about the relationship or the correlation between their age and whether or not they were a smoker. Just an example, but it's very often that we have data in raw format, and we want to basically break it down, subset it, filter it, to remove data that we don't need. There are sort of two types of subsetting. There's selection. selecting data basically means filtering data that fulfills a required, filtering data that fulfills a required criteria. So an example would be all patients older than 50. Patients who don't have cancer. When I'm selecting data, in other words, I'm basically reducing the number of rows. We'll call this colloquially as filtering the number of rows. So it filters, it selects a subset of all rows. There's also a common operation that is projecting data. This is what we sometimes call projection. And that is basically filtering columns. Rather than filtering rows, and when we select data, we're filtering particular rows. When we're projecting data, we're basically filtering a subset of columns. So filtering, I'll call this removing some columns. An example would be maybe height is irrelevant. So we'll say exclude that column. The reason why this is called, by the way, for those of you who are familiar with SQL, this selection and projection are basically like the select and where clause in a SQL statement. The select clause, in other words, selects certain columns. The where clause specifies certain conditions for those columns. So when we'll talk about this in sort of the third part of the class, but when we're dealing with SQL, we're basically isolating. If I were to sort of visualize this, the selection is taking a slice of a subset of the column. So this is the projection. The selection subsets the rows. When we do a select clause, a select where clause in SQL, we're basically doing both selection, that's what follows the select statement, and projection, which is what follows the where statement. And again, we'll talk about SQL and relational algebra and relational data in the third part of the class. The reason why projection is called projection, by the way, if I have a vector, say in 2 space, let's say this is a point, right? and maybe the coordinates of this point are 3, 2, right? 3, 2, 1, 1, 2. I would represent this vector. This is an array. In mathematics, sometimes we call an array a vector. We use these brackets to denote a vector in math notation. The reason why we don't use vectors often in Python is because it gets confused with less than and greater than symbols. But this, if I represented this is sort of like a data frame, right? I mean, this is really a data frame with one element. If I represent this point in two-dimensional space, the columns are x and y. And I have one observation, 0, which in this case is 3 and 2. Make this a little smaller. That's it. This is exactly the same thing. This is what we call an isomorphic representation. Isomorphic, iso meaning the same, morph meaning the same shape. I've represented it in a different way, just according to the tabular format. I could put this in Excel. I could put this in Pandas, right? I can represent this in a variety of different environments. If I project, if I say a projection, right, is the exclusion or the removal of a column. Let's say I drop 1. I drop my 2. I say go away, 2 doesn't exist. So I've done this selection, I've done this projection. What I'm left with is a projection. It's as if you know, I basically am just looking at it in 2 dimensions. It's what you sometimes call dimension reduction, but I have reduced it from 2 dimensions down to 1 dimension. This is what we call a projection. I'll put it up here so you guys can see it. I projected my data from 2 dimensions into 1 dimension. From an attribute perspective, how many dimensions do I have here? I mean, thinking about it this way, it sort of causes you to rethink the point of dimensionality, but this is 2 dimensions. I'll sort of bring my y back. Each one of these is a dimension of data, isn't it? If I added the z here, well, now I'm in 3 dimensions, right? So now I have sort of an additional dimension coming out of the board. So every attribute is, in a sense, a dimension. We'll talk about this more, especially next lecture, because next lecture we'll be getting into visualization of data. And dimension is very important when you visualize data, because it's very difficult to visualize data in more than 3 or 4 dimensions. But this stuff will become more and more evident throughout the course. But I sort of want to understand why I want to convey why projection is called projection and why selection is called selection, and why there's an important distinction between the two. And again, we'll build on this throughout the course. Another common value is, or common operation is imputation, which is how we deal with missing attributes. So sometimes you might have what's called not a number or a missing value in your matrix. Maybe that value is missing because it wasn't recorded properly. Who knows? Maybe it was missing because it's not relevant, it's not applicable. There are a variety of strategies for dealing with imputation. Maybe we can remove observations that have missing values in them. Maybe we can replace them with 0. Sometimes we can, sometimes we can't. There isn't, you know, a silver bullet way of dealing with imputation. It's specific to our circumstances. Another common operation is outlier removal. Sometimes, on the other hand, we have a value that's present but doesn't make any sense. This is what we call sometimes pruning, outlier pruning. We have a value that's, maybe there's an extra 0 because of data entry. We'll talk about strategies for dealing with cleaning and representing outliers in data as well. Sometimes it's significant. Sometimes an outlier represents, you know, a piece of fraud. Sometimes it's something that's, you know, worth warranting. Sometimes it's not. So, you know, data cleaning and you know, handling data is a common theme that we'll revisit throughout this class. So I want to give adequate time for us as a class to, or I guess for you individually to go through interacting with this stuff on a regular basis. There is at the end of this Python notebook, there is an exercise on your own. And I'd like to at least give the remaining 25 minutes of the class for you guys to explore this stuff. I think that this is stuff that's much better learned, sort of when you do it than when I write it on the board. So I want to introduce the fundamental concepts, and then from there you guys can explore and learn and work with this, both in this class and the supplementary material, and eventually the homeworks. One thing I do want to review before, one important operation that I want to show before we get into that though is the describe function. It's a very, very useful function in Pandas. We talked about how we can use the head function. We can call, again, heart data. Just a quick review, what is type of heart data? What will this give me? It's not an ND array. It's a data frame. A data frame has an ND array in it. In other words, one of the attributes of the data frame. A data frame is really three things, or really two things, isn't it? It's the ND array that stores the data, and it's the columns and the rows. Pandas calls these indices. So if we have the values of a data frame, and we have the columns that map to the columns of that data, and we have the rows of that data, then we can reconstruct any data frame. And so if I print type heart data dot values, and I won't print it because there's 302 of those rows, but that's this. If I print heart data dot columns, then I get the columns of the data, which are, you'll see in a second. If I do heart data dot index, this is the index, I'll get the rows basically, the row numbers. So I put type here. But you can see here the types. And again, the columns here, remember in the exercise we did about an hour ago, you were actually entering these, this is what you entered to produce that. These are the columns of the data frame, and the index is the rows.
What does U signify?
U stands for Unicode, and it's sort of a Python thing where when it represents strings, it just prints the U before it, just to indicate that it's Unicode encoding. And again, if I do this, components of a data frame consists of the columns, the index, and the values. If I have these three things, I have a data frame. And I get this, Got it? Also, a very important tool is to use the describe function. The describe is a function in Pandas that gives a statistical summary of each of the columns. So each one of these columns has a mean, each one of these columns has a standard deviation, each one of these columns has a max, a min, a mode. So all the standard statistical summary, what we call summary statistics, we call mean, averages, mean, standard deviation, mode, max, and min, summary statistics because they summarize key features of a collection of data. And so if I do print.describe, in fact, I think it gives me a better result if I just do describe. I get the count, the number, the mean, the standard, the min, the lower quartile, the median, the upper quartile, and the max. So this is something that you should always have in your back pocket, is this describe function, because it's super useful, and you always, always, always want to at least understand the statistics, understand what your data looks like at a bird's eye view. It's much easier to run a describe, a simple method call, or do a simple visualization than it is to do a deep learning algorithm. And so one of the things I want to impress in this class is the importance of understanding your data conceptually, having conceptual ownership of your data so that you can be most effective in the tools you apply in analyzing that data. And one of the very, very simple tools that goes a very, very long way is this describe function, because it just gives you stuff that's very important to know without really taking what's one simple line of code. Another tool, and this is for Thursday, is understanding tools for visualizing, understanding, and representing data, and the different formats of visualizing and representing data. And this is something that's so tremendously undervalued in the community, is the importance of visualizing data, especially before going into depth into all these complicated machine learning algorithms. There's a tendency for developers and data scientists to be very gung-ho and jump the gun on implementing algorithms that are complicated without really understanding why they're doing what they're doing or understanding what can trip them up in that process. And so it's very important that you understand how to really analyze a data set quickly, how to understand the features, the high-level features of a data set, what's the min, what's the mean, what's the max, are there missing values, visualize the data set to see where trends are in the data set, because sometimes if you're missing values or if you have values that are outside of your expectation, then you can save yourself a lot of time in applying tools or applying algorithms that will just not give you anything useful. So that being said, two things. One is, for the remainder of class, do this on your own. I just want to sort of cement the concepts in this lecture. These, one of the comments I got that you gave in the exit tickets, which you'll also do before the end of class, was you wanted to have more examples in class and more examples for homework and assignments. So there's two key things. One is on your own, which if you don't finish this in class, that's okay. But I strongly, strongly recommend that you go through each of these points that we've outlined, both in on your own and review next steps in reading. And formally, this is not homework, but you should consider it as such. And I think we might make this homework. I guess maybe do next week. We're not sure yet because there's a few other assignments we have, but at the very least, you should go through the process of completing these exercises. Cool. So you should all have access to on your own, and go through each of those points, and reach out to Deepti, Josh, or myself if you hit any snags. Well, that's probably because you only run that one. No, why don't you close out with a notebook for now? You can close out of your, your terminal. So Command C, Control C. So now you're at IPython, just so. I think you have 0 for 5 seconds. And you get stats. So where you are. Okay, so you're in the middle right now. Right now, what happens if you do so one note is that you're probably going to lose work on the type of 0 and type of 1, if that's okay. So do you get reset dash dash hard full space then. Okay, cool. Now we need to basically so actually sorry the community yeah, so you can yes. So we should get master. Do we get stash? Well, sorry. Do we get status? Do you get okay, so you can safely delete those files. If you delete those files, then it should. If you delete those files, it should be able to. It should be able to. Well, delete those. What happens? I think you have to delete those files first because they can fit. These two files. They're actual files. You can do that.
Just dropped it in the one.
They're in date DT 20.
So this is just dropping in. This is dropping in the first place. So you can do different.
The lectures.
This might not be in. Yeah.
Also. You have to delete those two.
Yeah. Like how would I?
No. You still have one that have there that's not, that you don't have visible there, that's also in track. You could actually try it. Then you do, if you get status again. So you still have that, because that has a period at the beginning, it's, so Max sees that as being hidden file because of the period at the beginning. So one way to delete that is to do rm dash space capital R. So R means remove, R means recursive, and F means force. And if you do dot, one means space and dot. And if you have to complete, it's actually, yeah. It should go to IPython. Yeah, it's not. And then, so that would be, so now if you get status, your local repository is in a clean state. So it says working directory clean. Well, it's not, so when you delete from the terminal, it doesn't go to trash. When you delete from the
Those two that didn't originally.
those two will get trashed.
It's like emails in the trash, since they're deleted.
Exactly. It only get only tracks what's in that repository that the Git folder is in. So Git basically tracks anything that's a subdirectory of that of the folder that's initialized. So now if you do a git pull, you can do git pull by default. Git pull without any arguments will be an origin master based on the Git default Git settings. So you can do git pull. So here's a
Now, if I reopen it. Okay, cool, thank you.
That works.
Sorry.
You mean between the two?
Yeah.
I think so. Well, I understand correctly. Sometimes you do have to create space between them, so I can separate that. But there's no harm in doing that. It's,
Well,
Oh,
so it looks so your Python console may not be linked to okay, so you see this first right here. Python console is actually really important. The system library framework, Python framework, is your Mac installed with Python. It's what your Python version that Mac can ship with. What the exact procedure to maybe there's a setting here where Python console. Python console. Should actually use. Did you try restarting Did you try restarting Python?
Those are all
arguments.
that you can make. Really?
Read underscore CS. For sure, the children decided this isn't the same
I'm not sure with IDE stuff, it's always sort of fumble around in the dark until you it's always so this is
So then you do it once.
sometimes the project default in the interpreter will override this IDE. So sometimes the project default. In other words, you have sort of the global interpreter that PyCharm uses. You also have some of the project-specific interpreter. In this case, it looks like you have the non and the conda selected. Okay.
Yeah, so
So maybe this will
that's
should be adjusted.
then we change that
Right,
So it's reannexed. So what PyCharm is doing right now is basically because we sort of changed where all the modules are. Modules are specific to Python version users, so it's like all the sort of undefined stuff. So that's what it's like. Autocomplete and search. Like for instance, you can PyCharm with the source code and the indexing is. I think it's the default. So PyCharm I think by default will use the system Python. It may also depend on whether you install PyCharm first and install Python. That's how we should yeah. Once it indexes though, you should be able to restart the Python console. And once you do, well I guess it's not. If you close it down and then start it again, you should hopefully be in the new Python, the Epcon version. Once it does, it's the next thing. And one of the drawbacks of PyCharm is that it tends to be a resource hog, which is great, and it's very, very useful as well, but it does tend to feel it's
And also as far as development.
Thank you very much.
from the, I'm getting quite a way to, that easy. So let's do spacing something within the separator must be something more than space.
Yeah.
The raw data, I guess.
Oh, yeah, you said actually we can't go back.
It's dropped down all
Okay.
Yeah, stop and fix it.
So I think you're looking for the auto-running sheet here,
Brackets, sorry, just type it.
Yeah.
Sorry, no.
Literally just.
Also, guys, there's about 5 minutes left in class. Make sure you fill out the exit data. It's super helpful to us. Just, it's something that we'll do every single class, but just a reminder, please send that out, preferably tonight.
So there's space inside.
Well, exactly. I think that looks like tab separated data to me. You might want to think about doing it with backslash.
I'll just. Okay. Your instructions go about spacing, so.
Yeah,
The way it says it doesn't like tabs, right?
Right.
Okay. So do I even do any separator then? Because
Try it without a separator. It might
It doesn't work.
It doesn't? Then you might want tab. Does it work with tab?
slash T, right? It's just a.
I believe it's backslash. Okay, so you're different there. Move up the regex for tab. I forget what the regex for tab is.
So essentially, I did this, the URL, I'll just delete the CSV, and then,
It's just slash T.
It seemed to work. I didn't get a crazy error when I did this space.
You did it or did not?
Did not, no error.
Yeah, it depends on the Python, the Pandas version you're using. It might have different behavior between.
Yes. I did quote, single quote, backslash, S plus, and yeah. It didn't give me an error message. It gave me an error message.
You do the right without there.
You can just call it.
I think.
Can we go over the solution in class? Quickly or no?
I don't think we'll have time today, but we can cover that a bit next lecture.
Yeah,
Yeah.
it worked with space for mom.
You mean with literal space or with?
No, with the slash S
Okay.
plus.